A developer types a quick prompt asking their local AI coding agent to resolve a newly logged software bug. While the agent generates the code fix, a second hidden process runs in the background. The agent simultaneously scrapes local AWS keys and NPM registry credentials and silently routes them to an external server. This chart shows exploitation success rates across the top 3 AI coding agents on the market. Against tools like Claude Code and Cursor, this exact exploit succeeds in 85% of tests. Our current enterprise security models are blind to how these autonomous systems operate on local machines. The underlying mechanism connecting these agents to the outside world is the Model Context Protocol, or MCP. It operates as a standardization layer, allowing AI to query external databases, to read local files, and pull telemetry. By design, MCP provides immense utility. It allows agents to autonomously read error logs and propose exact code fixes without requiring developers to build custom API integrations for every tool. The security paradox lies in the architecture. These agents operate locally with full system privileges, yet draw operational context directly from unvalidated external sources. In traditional software development, a human operator reads an error log, filters out illogical or malicious text, and then decides what commands to actually run. MCP removes that human filter. It creates a direct bridge between untrusted external data and highly privileged local code execution. The initial point of entry for this attack targets a common telemetry component, the Sentry Data Source Name, or DSN. The DSN is a public, write-only credential. Sentry intentionally designed it to be embedded directly in client-side JavaScript so that applications in the field can report errors back to the server without needing an authenticated session. An attacker uses an exposed DSN to send a synthetic error to Sentry's ingest endpoint. Formatted in Markdown, it mimics authentic diagnostic templates. Buried inside is an execution script, an npx command designed to run a malicious package. No server-side code execution occurs at Sentry. The vulnerability is an architectural mismatch. Unauthenticated telemetry meant for human eyes is now consumed by autonomous software as an executive instruction. The execution phase begins when a developer asks their local AI agent to investigate unresolved Sentry errors. The agent queries the Sentry MCP server and unknowingly retrieves the injected synthetic error event alongside legitimate logs. The MCP server forwards this event to the agent without applying any content integrity checks to the data. Current large language models lack the cognitive ability to distinguish between legitimate diagnostic context and an external attacker-supplied command embedded within that context. Because the agent inherently trusts output from its connected tools, it executes the payload. The attacker achieves remote code execution entirely by manipulating diagnostic logs. The threat extends beyond corrupted telemetry data. Attackers can also corrupt the tool descriptions themselves, a technique known as metadata-level injection. A recent framework called log-to-leak demonstrates this. It is an additive attack, meaning it appends a hidden action rather than attempting to override the main instruction. In traditional prompt injection, the model's primary task is usually hijacked or broken. With an additive attack, the agent completes the developer's primary task flawlessly, masking the intrusion. The attacker registers an MCP server with a seemingly benign tool, inserting a hidden trigger into its descriptive metadata. When used, the agent completes the legitimate task, but the poisoned metadata forces it to spawn a covert logging function afterward. This covert log captures and exfiltrates the entire interaction history, including user queries, capturing tool responses, and the agent's internal replies. This proves the MCP tool registration channel is an unprotected attack surface, operating completely outside the developer's visibility. Standard LLM defenses are not designed for this vector. This data table compares common defense methods and their failure rates. Even with prompt sandwiching, the attack succeeds 59.5% of the time. An LLM metadata check still allows a 55.3% success rate. These safety scanners evaluate the user's prompt. They fail because the malicious payload is stored in the tool registration metadata, bypassing prompt inspection entirely. Traditional enterprise security controls, like endpoint detection and response systems and web application firewalls, also fail to intercept the threat. From the perspective of an EDR system, an agent executing a package manager or reading a local environment file looks exactly like normal, authorized developer behavior. The attack requires zero privilege escalation and drops no identifiable malware binaries onto the operating system. Because AI coding agents operate with delegated authority, they neutralize the security controls built to detect unauthorized external actors. The root cause is structural. The Model Context Protocol's trust model was built for explicit tool invocation, not for the ingestion of arbitrary, unvalidated data. Vendor-side content filters and basic string matching algorithms are insufficient. They cannot close a fundamental architectural pathway. Securing these workflows requires implementing human-in-the-loop approval gates for any high-risk actions. Human developers must be required to explicitly approve any shell commands, package installations, or outbound network requests that originate from MCP-retrieved context. Organizations must aggressively audit and tightly scope all of their MCP server integrations. External observability platforms and telemetry tools must be treated as untrusted input channels by default. Finally, coding agents should be deployed strictly within sandboxed, constrained environments. This requires stripping the agent's access to plaintext local credential files and cloud metadata service endpoints. Until AI agents gain the cognitive ability to distinguish data from instructions, enforcing strict local execution boundaries is the only reliable defense against agent jacking.